Uh, when you have, let's say, two statements, A and B. Sometimes you say, if A, then B. That means if A is true, that necessarily implies that B is true. That's the statement. Or you could say, if B, then A. If B is true, then A is true. In the absence of any other information, those two things are not interchangeable. For example, the swan is white. Okay, that's a statement. If I see a swan, that statement says it is white. But if I see something white, that doesn't mean it's a swan. It could be a white cat. On the other hand, if and only if means those two statements are equivalent to each other. A is equal to A implies B and B implies A. For example, in this case, if I know that the bond value is equal to face value, I necessarily know that YTM is equal to coupon rate. Or if I know that YTM is equal to coupon rate, because of that if and only if sign, it's double-sided arrow, I know that bond value is equal to face value. So they're logically equivalent statements. Sometimes you know one of them, or you can show one of them, then you immediately know the other. This comes in a lot in mathematics. This is also kind of called characterization. Sometimes you can't prove that something is true on one end, so you go ahead and prove it on the other end. I'm just, any of you guys ever were interested in real analysis? Because it's basically fancy analysis of sequences and stuff. There's a concept called compactness of a set or a function. Typically proving that is hard. But there is also something called being sequentially compact. You can prove that relatively more easily. But there is another theorem that says any sequentially compact set is compact. So there's an if and only if statement. So I go ahead and prove one of them. It comes in a lot in statistical proofs. If any of you guys are interested in doing advanced statistics work. I know that sounds like, why would I ever need that? What do you think is the driving force behind the software end of the AI revolution? Anybody knows? We know the hardware parts. I mean, they just basically make fast chips that can handle big data sets. More than likely, they have multiple processors involved. For example, this computer has 16 processors. Technically speaking, 16 logical CPUs. That means any given task is internally divided into 16 pieces. If there is repetition, those 16 things are executed exactly at the same time. That's the whole parallel processing thing. The whole supercomputers, they have millions of processors. For example, one of the hardest problems in physics, even just with Newtonian physics, not even getting general relativity into place, is called the three-body problem. You can calculate orbits of a planet, given that you have on the sun and Earth, let's say. Solving the Newton's equation is not that difficult. And suddenly I introduce Venus into the picture. Okay, Venus and Earth are relatively close enough. They actually, exert gravity to each other. Solving for the exact path of Earth, Venus, and Sun is called a three-body problem. That problem is notoriously difficult. Only a supercomputer can solve it relatively precisely because the calculations required are much harder. If you have a supercomputer, you can do it. Solving Einstein's equations for specific cases is also very difficult. Years ago, back in 2003, I had just come back to US. I started my PhD at UK. And I had a pretty nice little computer because I was doing some fancy statistical work uh, for my brother-in-law, who also was a finance professor there. And one day I got an email from National Physical Institute, whatever. Can we use your computer online when you're not using it to make calculations? Basically, mine became a little server. Okay. When I'm not on, they connect it to my computer remotely, and they basically ask my computer to do simple stuff. That kind of means there's a central machine, and that central machine decides who's going to do what. I have 1,000 little slave computers, okay? And I have a task that I can divide into 1,000 pieces. So I'm going to say, you do this one, you do that one, you do that one. And as soon as you do that, you report to me the results. And the central computer actually puts them together. A lot of calculations, especially in general relativity, require stuff like that. And how do you think Google searches work? Do you think Google has a very big computer somewhere in California that does all the searches? No, these guys have server farms. In fact, most of those computers on server farms, they're very old, cheap computers because all they have to do is to be able to connect to the internet, get an instruction, carry that relatively fast, and report it back. It doesn't have to have 16 processors or 64 gig of memory. If they can handle simple stuff, even half a gig of memory would be enough. Those farms actually, those search business is very complicated. You're searching the entire internet, right? So you divide it into very little pieces and send it to these little minion computers and server farms. They look, they find or they don't, they report it back, and the algorithm puts them together. But going back, what is the driving force behind the AI revolution on the software side? It is the so-called machine learning, okay? And whether you do this for quantitative problems or you do this for generative AI, where based on the experiences, the software knows the patterns of people using a language and it tries to respond as a person. Whether they're doing that successfully yet, it's besides the point. For example, my son is working on machine learning models. It's called deep learning, where based on an EEG, you're trying to figure out whether the patient wanted to raise his arm up, down, or sideways, based on an EEG alone. Then you actually train that for an individual person. But initially, for example, the accuracy of that was 25%, and my son did something extra. That's now 40%, just initial accuracy. I'm sure they're going to keep improving that. Why? Because the model actually learns from that. And these are all actually statistical models. They're called neural network models, but they're basically specific nonlinear statistical models. So if you want to do anything in big data marketing or looking at financial data and figuring something out, you're going to have to learn machine learning models, which means statistics. So if you're going to be a marketing major and want to get a job that is different from just sales or ads, you better know some statistics. Otherwise, you won't be able to get those kinds of jobs. This is not 1990 anymore. Okay, we have so much data, and why do you think when you log on Facebook, two people get different ads? Because Facebook has an algorithm behind the scenes. It tries to predict what sort of things you would buy, and they show you exactly that one because that increases your chances of clicking on it, and they get paid by number of clicks and how many times they show it, but they get paid a lot more if you click on it. That's a statistical problem. Of course, it completely fails with me. Back in 2000, which you guys may or may not know, I'm a bleeding hard liberal, pinko commie. Okay, and when Trump started occupying the White House, I shall never call him president. Uh, you may remember there was a movement of the ladies. It was called the Pussy Hat movement. Okay, you had the hats that looked like the ears of the cats, and I had one of those. I even wore it on campus. And one of those pictures were on Facebook. Within 3 days, I started getting ads for gay underwear. Not that there's anything wrong with that, but you know, I bat for the home team, not the opposing team, in Seinfeld terms. So it didn't know what to do. I'm sure it's a little bit better now. But those models learn about your behavior over time. All right, the second one, we're going to call it the premium bond. That means bond value is greater than face value, hence the name premium. And that's going to happen if and only if YTM is less than 200.